All right, so we're going to talk about undefined behavior. My name is Chandler Carruth. I work at Google. I work on C++ for Google. I work on Clang and LLVM, the compilers. And one thing that I've done recently is I've started to try and talk with people about undefined behavior. So how many folks here are a little bit afraid of undefined behavior in their source code? Everybody. How many folks here think that this font is too small when it comes to talking about undefined behavior and how scared they are? Is that getting closer? All right, still too small. I mean, there are a lot of issues here, right? People are actually really kind of afraid of this, and I think it's something that we as a community need to try and deal with better. So that's what this talk is about. This talk is not going to try and justify all forms of undefined behavior. It's not going to try and remove all undefined behavior. The primary goal of this talk is to help us actually think about undefined behavior in a more productive way. Now, the number one thing I dislike about undefined behavior is this obsession with nasal demons, okay? Anyone recognize this, by the way, from the Infernal Dictionary? This is a demon, anyways. So I really don't like the idea of nasal demons because it gives the wrong idea, okay? And I understand where it came from. We wanted to convince people how serious the issue was, so we spoke in hyperbole, right? And the unfortunate thing is we've ended up in an argument about nasal demons with our users. And if you remember the keynote, right, when we're arguing, we're losing. And so the first thing that we need to do is we need to kind of dispense with all of this and actually have a discussion in practical terms and have an explanation instead of an argument, right? And actually, learn something about how this should work rather than just fighting. And you can see this, I think, best on Twitter, actually. So on Twitter, I've got all of these game programmers complaining that, we hear there's undefined behavior in libc somewhere, right? And then this escalates rapidly into, let's remove files from the hard drive, right? With the idea that this is somehow legal and an interesting example of undefined behavior. This isn't, okay? The compiler is not going to magically cause your program to suddenly make system calls that it never made before. Right? It's actually a very, very problematic kind of straw man that is put up. And of course, it's now kind of derailing the entire discussion. How can you argue with, not removing files from your hard drive? Okay? It's framing. Again, a reference to the keynote. So this continues to happen all over Twitter. James Woodman is really upset. He even kind of sent me a lot of tweets when I said I was going to give this talk. The idea that, so Marshall Clow has a comment about a male cat getting pregnant. I don't know what that's about. Again, your program can't do this. No amount of undefined behavior is going to cause that to change, right? Any more than your program can inscribe a summoning circle and raise a nasal demon. That actually can't happen. We do not, in fact, need an anti-nasal demon league. Then there's this email, and this is actually the email that really got me involved in this, because this one is actually very serious. This is from Dan Bernstein. All right? And here he says that, as a boring platform, and he's talking about the boring crypto platform that Dan Bernstein and several other cryptographers are driving right now, we need a C compiler that actually doesn't have undefined behavior. Right? And he's really serious about this. He's much more serious than I think anyone else who's arguing in this space is. Because when he says doesn't have undefined behavior, he means it. He means all undefined behavior. He means all implementation defined behavior. He means all portability differences between all platforms in the world. I actually got to sit down with Dan and argue with him about it. And really, he wants a virtual machine which behaves precisely the way an old 32-bit x86 Linux machine behaves today, and he wants that behavior forever so that they can run secure code on it. Now, that might actually be an interesting thing to build, right? And in fact, there are a bunch of programming languages that aim to provide this kind of portability, this kind of abstraction from the hardware. But I don't think that's C++, right? We're actually in the business of exposing the hardware, not abstracting the hardware completely away. We give you abstractions, but not that level of abstractions. So I think this really starts to underline the difference of perspectives that are actually happening here. And then you get to see some other fun things. So, for example, Jonathan Blow is a game developer. You may have heard of him. He's a very famous game developer. He built The Witness. He built Braid before that. And he's actually making a different argument. he's arguing that you don't need to work on undefined behavior sanitizers or other tools to help me with undefined behavior because it's your platform. You literally define the behavior. And in fact, you have to define some behavior for everything. So why are you dealing with undefined behavior? Just define it for your platform the way you have to and give me access to it, right? And this is a very interesting perspective because we've now gotten so lost in this undefined behavior that we're talking about hardware semantics and platform construction, and we've lost all sight of the programming language, right? We need to do something to this discussion to bring it back up to the programming language. So what are we even talking about with UB? What is UB in a really well-expressed way? And unfortunately, there's like a light right on my slide, but hopefully you guys can see this. So here is some UB. We have an integer pointer, we make it null, and we dereference it and read an integer out of it. This is undefined behavior. It's not particularly scary, it's not particularly interesting, but it's really boring, okay? Now, what I really like about this is that, we can check for this kind of error, right? This isn't hard to show that you've got a bug in your program. In fact, if you compile this code with Clang or GCC, you get warnings, right? They tell you, I don't know what you're trying to do, but it's not going to go well, okay? And there are even platforms which can check for this dynamically. This is a particular example of behavior that there are platforms which can give you a defined behavior. For example, on Windows, this code can be run with appropriate settings in your compiler, and it will produce very well-defined behavior. It will throw an exception. Okay? It's not rocket science. It's not the end of the world. The interesting thing is that there are platforms which have no mechanism for detecting this at runtime. There are even platforms where this is well-defined behavior at runtime. Okay? There are embedded platforms which have memory at address 0, and they let you dereference it, which is really concerning, right? So they may have no reasonable way to surface this very high-level undefined behavior to you on top of their low-level platform. And that makes it really challenging for the language to try and define this behavior because we may be, excluding ourselves from certain platforms the moment we do that. So the way I like to think about this is that this is actually a programming error. The language told me when you're going to dereference a pointer, it better not be null. And then me, the programmer, went and dereferenced a null pointer. That's my bug, okay? I should not have done that. This is just like calling an API out of contract, right? If the API, right, if we have this API and the contract says, hey, look, your pointer must not be null, and I call that function with a null pointer, I deserve exactly what I get. And I have no way of predicting what I will get. We're even going to standardize, hopefully, something that makes this even more explicit, right? We can spell this out. This API must not be called with a null pointer, okay? And once we spell it out in programmatic terms, we can build tools and other infrastructure to help check for any code I write which is out of contract, right? Now this is a really important thing. This means that my code is incorrect, right? Programming errors result in incorrect programs. And we can't define the behavior for all incorrect programs. Like this isn't in the cards. We could try, but we will fail. Okay? Now, I don't expect you just to believe me. That's lame. That's boring, okay? So let me try and convince you that we cannot define the behavior for all incorrect programs. Let's look at this program. We have a node, okay? This is a node in a directed graph. It's very boring, okay? This is extraordinarily boring. We have a node. It has outgoing edges. We have a routine. This routine finds a sink in a directed graph, but it will only work to find a sink in a directed acyclic graph. And it says so. It says there right there. It must be acyclic. You cannot pass a graph with cycles to it, all right? This is a fundamental thing. You can write this code in Java. You can write it in C++. You can write it in any programming language of your heart's desire. I don't care how much behavior it defines. If I pass a node to a directed graph with cycles, my program is incorrect. I have a programming error, and you cannot necessarily define its behavior. Let's look at the implementation to see why this is so hard to define behavior of. Maybe I define this implementation by recursive call. This is a valid and correct implementation of find sink. It will find async in the graph if the graph is acyclic. If the graph is not acyclic, this will do something very, very strange, okay? Depending on your platform, depending on various other things, this can do anything ranging from crashing your program due to running out of stack, throwing an exception due to encountering a guard page on a platform that can transform guard page violations into exceptions, okay? Or this could actually run forever. This could actually just never halt, all right? And if you want a guarantee from the implementation that you know, this is going to actually produce some defined behavior, you're gonna have a very hard time. So I've produced a directed graph. How many folks here know how to find a cycle in a directed graph? Hopefully a few people know how to find a cycle in a directed graph, right? We keep a stack, right? We keep a set of the things, right? We see if we encounter something we've already visited before. Haha, it's a cycle, we're done. But that's a lot of memory that this program doesn't use currently, okay? That's a lot of operations this program doesn't make. That might be completely unacceptable from a performance trade-off. And what's worse, I've chosen a very simple example I can put in a slide, right? And I've even got the iterative example, which will definitively run forever, all right? This will just never halt, right? But what if this weren't just a directed graph? And what if it weren't just finding a sink? What if this were evaluating a regular expression? Can we deterministically detect all errors in a regular expression? Probably. It gets harder, but probably. What if it's an extended regular expression that has a stack attached to it? That's called a push-down automata. We're now very close to needing a Turing machine to figure out if it halts, okay? Like, you cannot actually do this. You will run out of the ability to detect errors, and the trade-offs you're making in performance are insane here, okay? So what I want to point out is that we're not going to detect all errors in programs. Like, we can't. And what we're actually talking about when we see UB coming out of this programming error that we failed to detect somehow is a symptom, okay? That's all UB is. It's just a symptom, okay? It's like a headache. It's not the thing that's wrong. It's a symptom of the thing that's wrong, right? We need to talk to Dr. House about what you do with symptoms. I mean, sure, sometimes you treat a symptom, and it's important to have medications that treat symptoms. But you don't stop by treating the symptom. You need to understand what the underlying issue is, all right? And what I want to repeat over and over and over again, the underlying issue is not undefined behavior. Okay? It's not undefined behavior. There's a programming error somewhere that we were unable to detect. That's the underlying issue. I'm not trying to say that it isn't an issue. It is. It's absolutely a critical problem in software that we have programming errors we can't detect. But it's not undefined behavior that's the problem here. That's just the symptom. Okay. So the other kind of key realization is it comes from this idea of contracts. So we have code. It's using some C++ language feature out of contract. Now what do we usually call things which can be used out of contract? We say that they have a narrow contract. The standard library has been doing this for years and years, for decades now, Herb, I think. I don't remember when narrow contract went into the standard library. I haven't been on the committee that long. It's been in there for so long. We understand how to deal with wide contract and narrow contract APIs. What we need to do is start thinking about language features using the exact same terminology, the exact same methodology. We have a choice. We can make a narrow contract feature, which may cause problems, or a wide contract feature, which may have cost. But this doesn't explain one other kind of important thing here. Why is everyone so angry? All right, all I've given us is now some terminology and we can talk about things differently, but why are people so upset? The reason they're upset is because these contract violations that are kind of in their program are latent. They don't cause any problems for them right now. And I think that is actually our fault, okay? The fundamental thing that we, the standards committee, and we, the implementers, and we kind of library vendors have done that have worsened this is leaving these things as latent problems rather than making them manifest, right? Rather than making them actually patent problems visible to the developers. Because now, right, they look at this and they think like, well, look, I wrote my code, all right? I tested the daylights out of my code. I actually did my engineering job. I made certain that it worked. It worked so many times. It worked on different platforms. It worked everywhere. And then 5 years later, all of a sudden, something changes, some piece of infrastructure changes, and suddenly my code stops working. I used every tool you gave me to evaluate the correctness of my program, and every single one of them agreed that my software was correct. All right? I had no indication. What I had was a signal that the behavior of the software is predictable. and I assumed that minute was correct. All right? That doesn't actually follow. And that's why it's frustrating, because they've put in this effort, they have this kind of belief, but it isn't actually backed up by a strong commitment from the tooling. All right, so what can we do about this? So that's all kind of depressing and sad. What can we actually do to change things here? I mean, the obvious thing that about 18 million people on Twitter are asking me to do every single time I go on there is just define all the behavior. Just define all of it. So this is going to be really challenging. Remember that example with like the graph thing? I don't know how to define that behavior necessarily without an unacceptable performance trade-off. And if you give me, a Turing-complete language to interpret, I'm going to have a very hard time defining all of the behaviors. That will be extraordinarily challenging. So this is a tricky request. It also has kind of an unseen cost. Because if we go and define all of the behaviors here, we're going to inherently pick some behavior that works well on some platform. Like maybe I go off and I go to the standards committee and I write a really nice paper and I say, we're going to define all of the behaviors. And the definition I give them is what is really wonderful for me on my platform. Unfortunately, that is going to pessimize the behavior for a large number of C++ users. C++ is just a very diverse language, right? When I say that, like, so we're going to define all of the behaviors exactly the way they work on x86 64-bit processors, some of my wonderful colleagues who work on the ARM processors, they look at me and they're not really happy about this, okay? They're really not happy about this. Okay, so what this really comes down to is, can we make every language feature have a wide contract? That's what we're actually saying. We're saying define all the behaviors. Because we're not going to define the behavior of a Turing-complete language being interpreted. That's hard. But we could try and make all of these language features wide. Right? And this is the only response I'm going to get from a portability perspective when I try and do this. And it really comes down to a fundamental aspect of C++, right? C++ is supposed to make you pay for what you use. And so if we define particular behavior on one platform that pessimizes another platform, and the users on that platform aren't even benefiting from it, they're going to be very, very unhappy, and it's going to kind of undermine a core strength of C++, right? And what this really means is that this is a language which should not try and define all behavior. It can't, because doing so will pessimize some large body of its users, okay? So what we really want to do is we want to look at individual features. And we want to have a kind of careful evaluation. Should this feature have a wide contract? Should this feature have a narrow contract? Right? Like, what are the trade-offs that we should actually be using to make these assessments? The other kind of interesting question I get from a lot of people is, can we constrain the undefined behavior that comes out, right? I don't want my files on my hard drive to be, removed. I don't want, any kind of change to the nature of my cats. I don't even want a Schrodinger-like change to the nature of my cats. So can we at least kind of narrow the scope of what's going to go wrong here? Well, the problem with that idea is that this isn't about undefined behavior. Right? I mean, we could try and do this, right? And to a certain extent we have. As I said, I can assure you, your software is not going to change the state of your cats, okay? That's actually not in the cards. That's a straw man. But this isn't about undefined behavior. This is about how we define the semantic contracts for the programming language, all right? And so trying to focus overly much on constraining undefined behavior, I think, misses the point. What people kind of want to do is they want to have some of the behavior defined when we're out of contract. It's very like wishy-washy thing. And it always comes down to we have to pick what we're going to define, and our different users, like, they want different things. For example, my users, whenever something's out of contract, they usually want the program to stop immediately and to tell them that they've got a bug, right? But that's because my users can tolerate their programs doing that. I've got a bunch of other users, right, who are like, you cannot stop my program. If you stop my program, plane falls out of the sky. Don't do that, okay? And so they're in a very different situation. They can't afford for me to make the same kinds of trade-offs. This all comes back to the fundamental idea of C++, right? If we're going to make trade-offs, we have to be very, very careful that they don't pessimize users. So maybe what we really can focus on is this. When is it actually appropriate to have a narrow contract for a language feature? If we can't make undefined behavior somehow constrained, if we can't have all wide contracts, then we're going to need to think really carefully every time we add a language feature and we give it a narrow programming contract. right? Why would we even give programming language a narrow programming contract? Well, it's simpler, right? If you have a narrow contract, you actually have a simpler semantic model. It's easier to reason about. It's easier for humans to reason about. It's easier for static analysis tools to reason about. It's even easier to implement, right? This is one of the classic reasons why the standard library has some narrow contract APIs. They're much easier to implement than a wide contract API. If you have a wide contract, you have to have a way, without hurting performance in an unacceptable fashion, to check every single possible erroneous input to that API. And in a language feature, you have the same problem. Right? You have to be able to check every possible misuse of that language feature and produce a defined error. It's very, very challenging. And what's worse to me is that it also won't match expectations. Right? This is the other challenge we have here, is that if programmers expect a particular language feature to work a particular way, but they can abuse it, and as a consequence of that misuse of the language feature, we cannot give them the expected behavior. If we define a wide API, a wide contract, we have to give them some behavior. But it's not going to be something that they expect, right? And we remove the ability to say, no, look, this is a programming error. You simply should not have done that. That's a really kind of big loss for our programmers. So, was there a question? No, okay. So, we need some principles. We need some principles for how we want to do kind of narrow language contracts. Yes, question. There's a question.
Off the top of your head, can you give like an example of a wide and narrow contract in the standard?
Not only can I give you an example, I have a whole host of slides giving you those examples. About half of this talk is going to be staring at really complicated examples and thinking about how this applies to them. Okay, so we need the principles though to actually do that and to do that analysis. We need some principles for making kind of narrow language constructs. My first kind of dominant principle is it must be checkable. It doesn't have to be deterministically checkable, right? There are things we cannot check in a reasonable amount of time. It may not be checkable for all users or on all platforms, but we need to have some mechanism for actually checking whether programming errors are in the software, because that's what goes to the latent bugs. That's what goes to the anger and the resentment and the frustration of our users. When we give them a checkable tool, they can start to push back against that. They may still disagree with the trade-off between a narrow and a wide contract, but they're going to have that disagreement up front rather than it building into anger and resentment, okay? So that's the very first requirement for me. Second thing we need to have is we need to provide significant value. Not just some value, but significant value. Now this is always tricky, okay? Because different users, just like different users have different constraints, different users have different value functions, right? For some users, optimization is incredibly valuable. For other users, it's not the most important thing. Their code is already running fast enough. But we need at least some body of users that are benefiting from it. We can't just have narrow contracts because we want to, okay? We have to have a reason. We have to have some group we're helping by doing this. And it's not just about optimizations. I want to emphasize bug finding and simplification are good motivations to narrow a contract on a language feature. If we can find bugs in software, we will be doing everyone a service. The third constraint for me is that it needs to be easily explained. We need to have some rational model for telling our users, hey, look, here's the narrow contract on this API. Here's where you're going to go outside of that contract. Here's how to deal with that. Here's how to mentally model this language feature. If the mental model for the language feature ends up in direct contradiction to kind of the contract we give the language feature, our users are lost. They have no hope, okay? They have no hope. And finally, we can't have these narrow contracts when the entire world of software has already decided that that is an acceptable code pattern. We cannot just take widely violated principles of software and suddenly decide, you know what, we believe that there's a principled reason why all of that code is buggy, right? Because that isn't actually productive. We actually need to keep software that exists working. Okay, and I'm going to give examples that kind of touch on a lot of these different principles and show how they can apply and change things. Make sense? Questions before I go into examples? I really do want to emphasize when we get into the examples, please ask questions. These examples are sadly, they're not as simple as I would like because I wanted to give you guys examples that actually come up. All right, so the very first example, this one is at least fairly simple. Okay, so I've got a bunch of volatile and other stuff in here. This is so that if you go home and you like copy paste this into a compiler and run it, you will actually be able to see things happen. Otherwise, you get like compiler error messages because we statically prove that you have undefined behavior and we like throw out your program from the beginning. But this way you can actually kind of see what's going to happen when it executes. So we have an unsigned integer, not a signed integer, okay? And we have one of them at the value of 1 and one of them at the value of 33. And we are going to shift that 1 33 places. Now unsigned on my platform is 32 bits. And so this shifts the value by more bits than we have available. C++ says this is undefined behavior. This is undefined behavior even for an unsigned integer. And a lot of people are surprised by this undefined behavior. They don't understand, like, why does C++ need this to be undefined? This is actually undefined for portability reasons. We don't have a good way in hardware of implementing this operation in a portable, predictable fashion across platforms. PowerPC, x86, and ARM all implement shift left with a larger than bit width value differently, okay? Which can be very surprising. Okay, very, very surprising. And so we actually made this undefined because whether or not you intended this to be a programming error or intended this to do something useful, we believe it will be a programming error. Now there are some platforms that have tried to define the behavior of this. For example, the WebAssembly platform actually allows you to execute this code. The actual underlying hardware in the WebAssembly kind of virtual machine says that left shifts by more than the number of bits is fine. And as a consequence, shifting left by an unknown value is twice as expensive as it would be on the hardware because they have to pedantically check every single shift left on essentially every architecture in order to get the same behavior across them. All right, and this is really problematic. Yes, a question?
Why don't you call it implementation?
The question is, why don't you call it implementation defined? That's a great question. One problem of calling this implementation defined is because if we call it implementation defined, then I can't tell my users that this code is a bug. Because my users might say, like, no, I want it to work. I'm just relying on a particular implementation. By saying it's undefined behavior, we actually free the compiler vendors, right, to actually say, no, the contract of this operation is narrower because that's what we can implement efficiently and portably across architectures. And if you're outside of that, it is actually an error, and we can tell you about it. And it's not that we don't give you the expressive power to write the extra code necessary to get portable behavior, right? You can mask the right-hand side of this if you want. But we don't want you to pay for something you're not using, right? And if we did it a priori, you'd have to pay for it. Does that make sense?
You haven't broken my frame. Continue.
Okay. And I'm sorry, I'm going to try, but I understand. Okay, so then we have a more complicated example. Now this is actually like 5 examples. Don't panic. This is actually just 5 different examples. We're going to step through this. So the question that I have in this example is, how do I explain signed integer left shift to my users? Right? Because signed integer left shift has a narrow contract in C++. All right, you're not allowed to shift things off the top of a signed integer. It's just like integer overflow. So I need some way of explaining this to my users so that they understand how it works. The way I came up with, and the way several other people that work with me came up with was, okay, signed left shift is precisely analogous to multiplying by a power of 2. With one small caveat in that there are cases where you can't form that power of 2 in the bit width that you're actually doing the shift left, and we can just make that work, no problem, okay? It's just shorthand for signed multiplication. So we have on the left a shift left by 31, and on the right we do a multiply. So 1 shifted left by 31 is 2 to the 31, right? So this is the same. This is multiplying by a power of 2. This is shifting left. And the idea is we want these to be the same thing, okay? Now the C++ Standards Committee has chosen to actually define the result on the left-hand side here, which is really problematic because you actually have to use extra precision to get this. And now here we're actually doing a truncation from a value that changes its value. Before we actually assign this to a 32-bit integer on the right-hand side, we have a positive number. And after we assign it, we have a negative number. Okay, so the right-hand side here should be a bug in user's code. The left-hand side should be as well if we're using this as our mental model. But we've defined the left-hand side. We've even gone further. We've also defined the right-hand side for reasons I can't understand. I still have to complain to Richard Smith about this. But we don't even produce an error on the right-hand side right now. Okay, but that's a little concerning, but let's keep going. Maybe this gets better. Maybe this gets better. So the second example here, we have 2 bits set in our initial value, and we're going to shift it by 30. And we think, okay, so this should be equivalent to the same value multiplied by 2 to the 30, right? That's the mathematical model I'm supposed to be using. And I know, okay, that overflows a 32-bit integer, right? That's not going to be safe, so the shift left is also not going to be safe. And that's true today, okay? Then the third example, we have more bits, all right? And this one is interesting because we're actually shifting off the top of the value, all right? And this one again, right? We move it over to be multiplication by a power of 2. We note that multiplication by a power of 2 causes signed overflow, right? It exceeds the amount of precision we have available. And indeed, the left-hand side is also invalid. So this mental model works so far. Then we get to have some problems here. So what happens if I have -1 and I shift it left by 31? This is just completely undefined behavior. There's nothing here at all. And I find this really frustrating because while I have to extend, I have to have a larger integer in order to represent 2 to the 31 as a positive number. Once I multiply that by -1, I get a value which can be stored without loss of precision in a 32-bit signed integer, right? It's int min. There's nothing crazy here, all right? And so I have no idea why the left-hand side is not good and the right-hand side is good. I have absolutely no idea why this is the case. It breaks all of my mental model. And if you think that's bad, the second one is much worse, or the last one is much worse, because here I have -2, or not -2, it's supposed to be 0b11, it's supposed to be -3. All right, and if I shift this left by 30 bits, I should be multiplying, -2 by 2 to the 30, okay? And -2 times 2 to the 30 is a perfectly valid integer, right? I can do all of that in 32-bit integers. It produces exactly the result I would expect. There's no overflow. There's nothing wrong here. But the left-hand side is undefined behavior. The right-hand side is defined behavior. So I don't have a mental model to explain this to my users. This is a really bad narrow contract in the language, okay? If we want this sign shift left to be a narrow contract, my suggestion is we make it work the way it works on the right-hand side, precisely, okay? And that may mean removing something we actually defined in order to allow you to compute int min, but it will also mean adding back something, x4, which is a much more, in my opinion, mathematically sane way to compute int min, and it is exactly 1 character longer, so I think that's an acceptable trade-off. But unfortunately, the committee actually looked at this and we got it wrong. All right, and it wasn't our fault. It wasn't that we didn't try very hard. We tried very hard. There were hours and hours and hours of debate on this in the committee. Lots of people sat and looked at this, and we all missed it. A large part of why we missed it is we weren't thinking about what's the contract of integer shift left, signed integer shift left. What is the API? How do we explain this to users? We instead were just looking at that top example and wondering whether we should make it well-defined. So I think this explanation thing is really important. Questions about these examples? All right. So this is one of my favorite examples. This code comes out of a very old version of GCC that is part of Spec. Anyone here familiar with Spec? Anyone here not familiar with Spec? Cool. So Spec is this huge benchmarking package, right? A group of people collect open source programs and kind of refine them into very predictable forms and package them as a set of correctness tests for compilers and benchmarks for optimizing compilers that are common across the industry. Lots of people use them, all right? And several academic researchers, including Will Dietz, John Reger, Vikram Adva, and one of the person whose name eludes me at the moment, did a wonderful piece of research about integer overflow. And the body of software they looked at was actually all of the software packages in this Spec benchmark library. They weren't benchmarking, they were looking at correctness issues. And in GCC, an old version of GCC was actually added to this benchmark library. And this is some code from GCC. It's an allocation routine, okay? And so I've tried to give you some hints about how to interpret this. We have 2 structures here, RTDef and RTUnion. The size of RTVecDef is 16. The size of RTUnion is 8, okay? Now this is only using undefined integer arithmetic here. There's no, unsigned integer arithmetic here. There are no signed integers. There's no signed integer overflow here. This has well-defined behavior for every execution that occurs in spec. But it isn't correct for every execution that occurs in spec. So one of the spec tests actually calls this routine with the value of 0 for in. And if you call this routine with the value of 0 for in, you get a very surprising result. It took them a lot of time to understand what was going on here. So the key thing is that inside of this structure, we have one element of an array of RT unions already inside the structure. So this allocation routine is trying to allocate the remaining elements in that array, okay? But if you don't need any elements, if the size you need is 0, and that actually happens in like the run of GCC inside of spec, then you come down here and you take 0 minus 1, and that's -1. Okay, that's fine. But then you multiply it by an unsigned integer, because size of produces an unsigned integer. And the result of that is very surprising, because the first thing we do is we convert -1 to an unsigned integer. And that doesn't produce the unsigned integer that essentially anyone wants it to. Okay? It produces an enormous unsigned integer. We multiply it by the size of RT union. Now, you might expect this to kind of fail catastrophically and immediately, but it doesn't. Because you see, unsigned integer multiplication is well defined on overflow. And -1 produces a very large unsigned number. And so when we multiply it by 8, it immediately overflows. Okay, and produces a very small number. which is quite unfortunate. And we add it to the other size. This goes on to actually create a memory safety error in this program, okay? And this is despite the fact that this only has defined integer arithmetic. And this goes to a point about narrow contracts, okay? Sometimes a wide contract isn't what you, the programmer, wanted, right? If we had a narrow contract here, I could build you a tool, okay? I could build you a tool that would tell you, hey, you have a programming error here. There is no way you intended n-1 times size of to overflow an unsigned integer, wrap around, and produce a small value. Like, there is no way that was a correct thing. You were expecting basic, like, infinitely precise integer arithmetic to hold. And instead, you got modular arithmetic on a modulus you never saw coming, okay? Like, there's not even, like, we didn't even write an unsigned type in this function. It just snuck in and bit us. So narrow contracts actually have their purpose for bug finding, right? They actually help us identify software bugs. And one thing that I've talked about elsewhere is Google actually looked very carefully at our source code and considered defining signed integer arithmetic. And one thing we did was we just before we define it, we can turn it into a checked integer arithmetic routine, right? And we can go and look at all the places that check fires. And we can see if defining the behavior in some way would cause the code to be correct. And there were places where it would cause the code to be correct. But there were also hundreds and hundreds and hundreds of basic arithmetic errors, just like this, which if we give them defined behavior, will stay bugs in the code forever, and we will have no way of finding them, all right? To give you a very precise idea of how powerful having these narrow contracts and checking them can be, the Android folks have now actually released a version of Android which turns on signed integer overflow checking in a large number of the software packages on it, so that your phone actually is checking this because they looked at the performance numbers and they looked at the security risks, and they're like, oh no, this is a clear win. We aren't having really huge problems with our integer arithmetic throughput on the processor. We are having really huge security problems. This is a no-brainer. We're going to turn on checking. And because we can turn it on inside the toolchain, because it's a narrow contract that we can systematically enforce across the entire program, it's very easy to kind of get rigid checking that checks every single overflow chance. We don't have to teach programmers how to do correct overflow checking, which has proven to be very, very hard, all right? Any questions about this example? All right, next example. I also want to give an example of optimization. There was a whole talk earlier this week about kind of optimizations that fall out of kind of narrow contracts that the compiler can make very profitable transformations based on. This one, though, is my personal pet favorite, because it's one that every single compiler and optimizer engineer I have talked to never saw coming. They all knew about all of the other optimization things. It's well studied. This one they did not see coming. And this is also fairly real code. So I mentioned Spec earlier. One of the applications in Spec is actually fairly widely known. How many folks here have heard of bzip? Anyone? Cool. This is a function in bzip. It's actually a really tiny snippet of a function in bzip. But this actually comes out of bzip. Okay? And this is actually in a very hot part of bzip. It's part of a quadratic algorithm inside of bzip that it tries to do for a little while because it's very profitable for compression, but very expensive. Okay, and so this is a very important performance-sensitive piece of code in bzip. I also have these ... dots here. An important thing to realize is that this goes on, this 1 and then 2, we get up to 12, and then we start looping. Okay, and then we have another 12 inside the loop, and we loop for a long time. So I'm just showing 2 examples here, but this is actually a repeated pattern that happens throughout this entire function. Okay, and what we're doing is we're extracting 2 characters, right, two bytes of data. We are comparing them, and if they're not equal, then we've determined that this is greater than, and we return the greater than state. This is just a comparison function. All of this is the implementation of a sort algorithm, all right? And you wouldn't expect a sort algorithm to really suffer from optimization challenges to do with narrow contracts versus wide contracts. But this code was written using unsigned integers. And one of the reasons it was probably written using unsigned integers is to get that wide contract. Okay, to get no, any value we use here, it'll be well defined. We don't have negative numbers, we don't want undefined behavior, we're gonna use an unsigned integer. And as a consequence, we get this code on the right-hand side here. And this code on the right-hand side, I don't know if you guys read a lot of x86 assembly, but the code on the right-hand side is terrible, atrociously bad. So I'm gonna skip right ahead and show you what the code should look like. So if we just take these 2 U's out of this signature and make them signed 32-bit integers, we get this instruction sequence. This instruction sequence versus that one. There's a small difference here, okay? Now what happened? That was the immediate question people asked me when I showed them this. They couldn't believe that this was actually that big of a problem. So what's actually going on here is that we have these 32-bit integers. And the 30-bit integers are used as array indices here, okay? When you use a 30-bit integer as array index, right, what you're actually doing is you're taking the array, which is actually a pointer, right, at the hardware level here, this is a pointer, all right? And you're taking this index, and you're gonna scale that index by some value, okay, in this case, 4, all right? Or sorry, in this case, 1, so it's easy. Some cases you have 2 or 3 or 4. And then you're going to add that scaled value to your pointer, and then you're going to dereference that to load the value. Does that make sense? Now, this is so common that x86 has a special hardware feature to do precisely this, okay? And in fact, the other thing that's so common is that you do first 1, and then you add 1 to each index here, and then you do it again. And 2 then adds 1 more, and then we do it again, and again, 12 times. And then we do another 12 inside of a loop. So common, x86 has lots of features to help you with this. You can actually add a constant offset. You can scale things. You can do all of this very nicely. But there's one problem here. If, for any reason, this +1 down here overflows, okay? In 32-bit, it has to wrap to a 30-bit number. And if that happens, right, it's going to be a very different value. But this is a 64-bit architecture that I compiled the code on. So the pointers are 64 bits, but the indices are 32 bits. This happens all the time in real code, right? Because you don't need 64 bits of index, you only need 32 bits. It makes your data structure smaller. It happens very, very frequently in real code. And so in order to implement that in x86, we actually have to use a different set of instructions. This LEA-L, right? And what this L over here means is that we're restricting this to a 32-bit computation. So I put it into EAX. 32-bit register, all right? This gets us the 32-bit wrapping behavior. That's all it's doing, is getting us this 32-bit wrapping behavior. Because if we got the instruction we wanted down here, if we just folded this into the address computation to load the value out of memory, we wouldn't wrap it 32 bits, we would wrap it 64 bits, because it's a 64-bit pointer. Okay, and we get a completely different answer. Now it happens that in this program, the programmer didn't need 2 to the 31 modulus behavior. That wasn't what they were interested in, right? They were actually interested in just having an integer. And so this actually slows down, this actually causes this inner loop of bzip2 to have over twice as many instructions as it needs to just because we used an unsigned integer when we didn't need that extra precision, we didn't need modular arithmetic, but we were a little bit worried about a narrow contract, right? Narrow contracts are simpler. They do actually allow you to make very impactful transformations. It's not just about loop analysis or other things. All right. Any questions about this crazy example? Yes?
I don't see integers with increased on the right side of the
Can you repeat that one more time for me?
E1 and E2, where do they get increased in the right side of the slide?
In this one. So the question is, where is I1 and I2 being increased? This 1 right here adds 1. I understand that this syntax, 1 outside of a parenthesis, is a very strange syntax for addition. But I assure you that that's adding 1. This is adding 1. And if I kept going past 2, you would see a 2 outside of the parentheses, and then a 3, and then a 4, and then a 5. Yeah, we essentially delay actually modifying the register because we can, which also makes this much more out of order friendly. We can execute this in parallel. Another question at the back, I think.
Why is size t undefined, unsigned?
Why is size t unsigned? That, sir, is a story of much sorrow. So a long time ago, we didn't have enough bits. And we saw there was 1 bit we could steal. And so we did. It was important. It was probably the right call at the time, right? Today, we have a lot more bits. It's not clear that that was the right call now. Also at the time, there was a lot of thought around, there aren't negative sizes. It doesn't make sense to actually have a type with negative sizes. I can actually see a pretty compelling argument for having an unsigned integer type which has undefined behavior, which has a narrow contract, there we go, which is a narrow contract on overflow and underflow, and a separate unsigned type which has a wide contract and provides modular arithmetic. I think they're both reasonable things to want to have. The value of having the unsigned type separate from the signed type, both of them with that narrow, mathematically derived kind of contract, I think is much smaller today than it was a long time ago, because today it's fairly easy to get enough bits without having to use the sign bit. Yes?
So if instead of in 32t, we would have written size t, and it resulted in the same.
Yes. If you use size t, that will also avoid the problem. The downside to using size t is that if this parameter isn't a function parameter, but is in fact in a data structure, it uses more space. And in this particular case, I didn't show the caller. In the particular case, we get these indices out of a data structure. And so they are actually small values in that data structure. We could extend them to 64 bits ahead of time, but that's really just moving the narrow contract assumption from this code to the caller, right? It's not changing the trade-off there. Yes?
Isn't this just a failure of the optimizer to do the right thing?
No, we cannot produce this assembly for this function. It is incorrect, it is invalid. Absolutely invalid, because this might actually wrap this 32-bit I1 from a very large number, from uint max to 0. And we have to use this instruction to get that wrapping behavior. If we use this instruction, we will not get that wrapping behavior. They are different. They are semantically different.
But that wraps as well.
No, this wraps at 64 bits, not at 32 bits. That doesn't, yes, this is why it has to be a signed 32-bit integer.
Yeah, but still in 32 bits.
So this is still 32-bit integer, but we take advantage of the fact we know it doesn't wrap to promote it to a 64-bit integer and use it as an operand to a 64-bit addressing mode. This is a 64-bit address. This is a 64-bit extension of that integer. So we've changed the semantics here. And the only reason the semantic change is legal is because it was signed and it has a narrow contract which says it doesn't wrap. Otherwise, we would give you the wrong answer. Happy to step through this again.
Yeah, I think I'll take it offline.
Okay. Yes, another question.
How would you recommend to avoid problems like this?
One more time.
How would you recommend us to avoid problems like this? Detect them.
How would I recommend that we avoid problems like this? If you have an integer which you want to treat arithmetically, as opposed to in some modular space on some power of 2, make it signed. If you need more bits, get more bits. Keep it signed. It's very straightforward.
You'll have the same affect if you just int.
Say it one more time.
You'll have the same wrapping affect using only int.
The comment is that this will have the same behavior if we just use int instead of int32t. I kept it at int32t to kind of show that it's still a 32-bit integer, just now signed, and that frees us in the implementation. Yes?
I give out the same advice that you just did, but I'm arguing and I'm losing.
Yes.
Let me do it.
So you have two choices here. One of them is that you can let someone like Titus do it, who enjoys losing. The other alternative is that I don't make this as an argument, right? I only say this when someone asks me the question, how can I avoid this performance problem? Well, here's how we can fix the performance problem, and we can do it in a safe, systematic way. Make sense? It's the best advice I have. And it's the same advice that we got at the keynote is, start with the discussion, wait till there's a problem surfaced, provide, constructive suggestion rather than an argument. More questions about this? I'll take one more.
One more is, well, what if you compile on another platform where using signed integer causes the performance degradation, and unsigned is actually
So the question here is, what if you compile on a platform where a signed integer actually has the performance problem? This is not platform specific. The opportunity to make the code faster is platform specific, but the nature of the change is actually platform independent. Every platform, signed will be the fastest alternative. Like you've got like a compiler author guarantee. There are compilers which are stronger or weaker, but I don't know of any compiler which fails to optimize a signed integer but successfully optimizes an unsigned integer. It doesn't make sense because it's always valid to just like it's a strictly more constrained, a strictly narrower contract. Does that make sense? All right, let's keep on. I want to at least talk about one more example here because I don't actually think C++ is getting all of this right. I'm okay on time. So here's an example that I think is really bad because C++ gets this one wrong in my opinion. So here we have a signed integer, and again I've put the 32 in here just to make it incredibly explicit that there's a very specific bit width taking place here. And I would like to shift right. Now what does this mean? How many folks think this is well-defined behavior? You're all wrong. Okay, you got a couple hands, good. This is well-defined behavior. How many people know what this does? No one. Oh, only one person? I don't know what this does. This is implementation-defined behavior, to the comment earlier. This is actually implementation-defined behavior, but I don't know which implementation-defined behavior. Okay, I have no idea which implementation-defined behavior I get. And that's very frustrating for me because what I'm trying to do is a very specific, very well documented operation. I would like to do an arithmetic shift to the right, which on a 2's complement machine leaves the sign bit in place and copies it downward through my bits, okay? So this creates, for example, a 8-bit mask at the top of my 32-bit integer. This is incredibly useful. In fact, essentially every cryptographic algorithm in the world has this code in it hundreds and hundreds and hundreds of times. And every single one of them, I don't know what the semantics of that algorithm is because there's implementation-defined behavior. We are allowed to implement this using sign magnitude signed integers instead of 2's complement. And I have no idea what shifting right on a signed magnitude integer does. I literally have no idea. And no one else does either. No one on the committee knows how this is supposed to work either. We just have this implementation-defined behavior rather than actually giving it defined behavior. This is a really big problem with our kind of persistent attachment to supporting more than 2's complement arithmetic. It is not really compatible. We need to pick a single mathematical model for arithmetic here. I think that the obvious choice in this day and age is 2's complement, and with 2's complement, this has very clear semantics. It should be well defined and should give me an arithmetic shift. Every single processor that I use today has an arithmetic shift right. It is unacceptable that there is no way in portable, conforming C++ code to produce an arithmetic shift right instruction on a processor. Think about that for a minute. There's an instruction you cannot produce using portable, conforming C++ code on every single architecture in the world today. It's mind-blowing. And this is the problem, right, that people are having with C++'s narrow contracts. right? It's not actually that they're opposed to the idea of a narrow contract, it's that we've got a bunch of narrow contracts that are really bad ideas. Okay, this one is probably the worst example I have. How many folks recognize this example? So this is the subject of, I don't know how many security vulnerability reports over the last 5 years. Here we have 2 null pointers and a 0 size passed to memcopy. I am not aware of a single memcopy implementation in the world on any platform, on any hardware architecture, on any libc, anywhere that doesn't implement this correctly. However, the C standard says that the destination and the source shall not be null. That's what it says in the standard. I can't argue with that. It's been there for decades. However, people didn't really notice for a long time. And I mean, like, really didn't notice for a long time. Okay, about 10 years ago, one platform started annotating their header file to say, hey, by the way, you can't put a null pointer here. And that was fine. No one paid any attention to it because it didn't do anything. It was just some text in a header file that no one read. And then, a few years later, this got released more widely, and eventually some compilers started seeing this annotation. And they're like, hey, you narrowed the contract. Cool, that's awesome, I'll help you out, right? Sometimes the compiler would insert a trap if you send a null pointer through that thing. Other times, it would delete all of the null checks further down the code. All of them. Okay, this was a really bad idea. It's not a bad idea because having this narrow contract is fundamentally a bad idea. This is a plausible narrow contract if there's some huge reason. It's because this satisfies not one of our principles for a narrow contract, okay? It may be checkable, but it was unchecked forever, okay? So that means that everyone was like, well, my code seems correct. Number 2, this provides no value. Every implementation, despite memcopy being one of the hottest pieces of code ever executed on any CPU, no one ever needed to leverage this narrow contract to make anything faster. I'm not aware of any bugs caught by this. I'm not aware of any value whatsoever that this narrow contract provides. It also is very hard to explain because it doesn't actually make sense. You get it at 0, you're not going to read the memory. I don't know why it matters what pointers you give it, okay? And in fact, it violates the last principle of every piece of code everywhere did this. Like, why are we changing it, okay? And so we do get it wrong sometimes. But I think that it becomes a lot more clear that we get it wrong when you explain things in terms of narrow contracts and wide contracts, and you take a very principled approach to how you justify your narrow contracts. And with that, I am 1.5 minutes over time, but I'll happily stick around for some questions or see you outside. Thank you very much.